Okay, we're going to get started here. So we're off to, I think it's chapter 5. And in chapter 5 here, we're going to talk really about naming. Pretty much all the naming you ever want to know about. And we're going to talk about ionic naming, molecular naming. We're going to talk about how to name acids. Naming involves polyatomic ions. All right, so again, this should be chapter 5, and this obviously will help us with the lab that's going on. So let us get into it. So nomenclature is really, it's a fancy word for really how we go about naming everything and naming compounds. It's good to remind ourselves of, especially with ionic compounds that obviously have ions involved, that there are certain guys on the periodic table, as I think we've talked about before, that have, fixed charges. So everybody in group 1 will have a +1 charge. Everybody in group 2, guys, keep it quiet, please. Thank you. Guys in group 2 will have a +2 charge. Skipping again our transition metal region, which is in the middle here. That is group 3. We'll have a +3 charge. Really, it's aluminum there. We're talking about off the periodic table. Right around here, right? We got that staircase that kind of comes down on the periodic table. Group 4, there's really not a great pattern because, again, above the staircase, you got non-metals, you got metalloids on the staircase, and below you got metals happening. Then starting with group 5, up in the non-metal region, which is up and to the right of the periodic table, that's going to be -3. Group 6 will be -2. And group 7 here will be -1. So these guys have fixed charges on the periodic table. Our transition metals, which are here in the middle, they have a variable type of charge, which when we go to name these type of guys that have those, we do have to do some additional things with the naming. There are 3, though, that are in the transition metal region, which even though they are transition metals, they still have fixed charges. And that is our friends here, zinc and cadmium. When they do form a charge, it is going to be +2. Hang a left there at cadmium and go to silver. Silver there will have a +1 charge. So these 3 sort of transition metals here, just like backwards L right there, even though they are transition metals, they also will have a fixed charge. So that's important to remember. That again leaves us pretty much everybody else in the transition metal region will have a variable charge. And in addition, even though they're technically not transition metals, also in this area of the periodic table, kind of below the staircase, these are metals. And these are guys like lead, tin, antimony in that particular place. These guys also have variable type charges. So they're sort of, as we will see and as we will talk about, even though they're technically not transition metals, they're sort of grouped with transition metals when we name them in terms of how we go about naming them, because they do have that sort of fixed sort of charge. Any questions on that there? Okay. So in general, when we talk about ions, which are things that have charges, as we talked about before, there's really 2 types. There are cations, which we will see, that have positive charges, and there are anions, which have negative charges. And if we happen to just have the ion by itself, an important part of naming is if it is a positive ion, we pretty much just use the whole name of the ion here, or the metal, really. I guess it's the better way of putting that. So for example, if we had Na+, and again, if we were to write the formula for a cation, it should have a charge because it is an ion. So you should include the charge here. If it's just sodium ion by itself, that is what we would call just the whole name there, which would be the sodium ion. Doesn't matter the charge, if you had a calcium here with a +2 charge, this would be the calcium ion. Now, nonmetals sort of work the same way. We sort of use the root of a good part of the nonmetal name, but we do end up dropping the last part of the name and we put IDE at the end of it. So if we had something like Br minus, which again, just by itself, Br minus there has the charge, we would want to write the charge, and instead of bromine, it becomes the bromide IDE ion. Same thing with something like oxygen with a -2 charge. If it was just the oxygen ion there, with the -2 charge, we would drop the last part of oxygen. It becomes the oxide ion. Sulfur as well becomes the sulfide ion. So these two guys, especially when we're talking here, and we're going to open up with these guys, I think in terms of ionic compounds, it's pretty simple. The positive guy, pretty much you just use the whole name. The negative guy, pretty much drop the last part of the name, put the IDE at the end of it. And there are some other sort of rules when we're dealing with different ones here. But if you're just writing the formula for an ion, so if you're asked to write the formula for the cation by itself or the anion by itself, they should have charges because they're ions. And again, this is how you would go about sort of naming those guys. Any questions on that there? Yeah. Now, there are certain things, as we will talk about, that really do go by common names. And really, I would think, truthfully, the first three here really are the most important here. H2O is water. It is not a trick question. When you see H2O, you should call it water. Nobody wants a refreshing glass of dihydrogen monoxide, right? So you should really just call it water. Weird names that people call it. NH3 is what is known as ammonia. It's a weak base. And CH4 is the simplest sort of organic guy you could have, and that is known as methane. It's like the stuff that comes out when we light the Bunsen burner. Truthfully, most people don't really call this table salt. Most people still refer to it by its sort of proper name, which is sodium chloride and table sugar. So I would say for us, definitely these three here, you should always go by the common names: water, ammonia, and methane for sure here. So let's talk a little bit about going about naming these type of compounds. And first, we're going to talk about really binary compounds. And there's really two sort of groups of binary compounds that we sort of come across. First one is one that contains a metal and a non-metal. And as we talked about with bonding, whenever we have a metal and a non-metal, those are going to result in an ionic compound. And that is where we're going to really get those ions of positive charge and negative charge is going to occur. This is where we got our cation and our anion happening. And as we talked about with bonding, really no sharing of electrons in this guy, right? So we get that full transfer of electrons from the cation to the anion, as we talked about in bonding. And that results in these guys that have a positive and negative charge, which is what holds that together, that unit. The other type of naming we're really going to focus in on as well is when we do get sort of covalent bonding happening with molecular compounds. And that's when we have really two nonmetals together, sort of covalent, if you will, where we do have sharing of electrons. And as we talked about in bonding, this again results because they are really all nonmetals there, which means they have very similar periodic trends, which means really neither one of them wants to give away their electrons. So they do want to end up sharing electrons. So there is slightly a different way in which we name it. Just like what we talked about with bonding, in a covalent compound, there are no ions. So, there's really no ions that are there. So nothing with sort of charges, except for the maybe polyatomic ions, which are kind of like covalent molecules that have charges. So depending on whether it's ionic and depending on whether it is sort of a molecular or covalent sort of compound, there are different ways that we go about naming these guys. So we're going to start with really ionic compounds. And these guys are sometimes referred to as type 1 and type 2 compounds, and these are ionic. And pretty much there's a couple important things to remember, and I think we touched upon this in an earlier chapter as well, that when we have an ionic compound which contains a positive and negative guy that comes together, there's a couple of rules that we always follow. The first one is it's always the cation followed by the anion, so positive followed by negative, both when you write the formula and when you name it. So both in naming and writing the formula, should always be this sort of formula here, positive guy followed by negative guy. The other important thing is, as we talked about, whenever we take a positive guy and a negative guy, when we do put them together, the goal here is to get it to an overall charge of 0 in the easiest, I won't say easiest, in the simplest way that you could do that. So the simplest way that you could get an overall charge of 0 is what you want to do. And as we talked about in bonding, really the purpose of this, right, is for everybody to achieve that noble gas configuration. And in this case, obviously, we would need more fluorines to give us, like we saw, I think we drew this guy when we were doing Lewis structures, the calcium fluoride here. So when we do write an actual formula for an ionic compound that contains both the positive ion and negative ion together, the actual formula should never, ever have a charge when it's put together. It should always equal 0. But it's important to remember that even though the overall charge here is 0, it is still made up of things that obviously do have charges. So it is still made up really of ions. We just represent it in the ionic formula with no overall charge. And again, to balance it out to 0 in the simplest way possible. Any questions on that? Yeah. We're going to actually talk about it, but they are types of ionic compounds. And as we'll see in just a slide or two, basically the difference between them is the type of metal that's involved in those guys. Other questions? Okay. So let's talk about that. So whenever you got a metal and a non-metal together and you're interested in naming, which is always what you get when you get an ionic compound, between both of those, it is always the metal that is most important. So it is always the metal that is the most important. It is the one that really determines how you should go about naming them. And that is, as to your question, what type 1 and type 2 refers to. Type 1 refers to a metal that basically has a fixed charge. So as we just talked about at the beginning, those are our guys in group 1, 2, and 3 on the periodic table. And also those few transition metals that always have fixed charges, like our zinc, our cadmium, and our silver. So once you sort of identify the metal as being in one of those groups, you could identify that as a type 1 compound. And we're going to talk about here in just a second how you go about naming that. A type 2 compound, again, you always want to look at the metal. Most important, whenever a metal is involved, it really is sort of the most important in terms of the naming part of it. And a type 2 metal is basically the rest of the metals that are there. Those are our transition metals. And just to the right, as I drew on that sort of periodic table a minute ago, these are the guys that have variable charges. And we're talking again about the metal. So the metal could have different positive charges depending on the situation. So for example, here we look at chromium. Chromium could be +2 or +3 in certain situations. Copper, for example, here can be +1 or +2 in other situations, depending on what is there. So the way we name these two guys, or the differences in how we name these two guys, are very simple, except that because type 2 basically has a variable charge, we do have to let people know sort of what the charge of the metal is. And we have to do an extra sort of step there when we go about naming them. So let's take a look at each of these a little bit closer. First off, before we get into that, since we're talking about ionic compounds, as I said on the earlier slide, if you have any positive ion, you basically just use the whole name. As you can see over here, these are all cations by themselves. It is the anions that we put the IDE on it, and our good friend hydrogen, which has a lot of special type of properties, as you can see, actually can go both ways. You can have hydrogen that is positively charged. You can have hydrogen that is negatively charged. The only time really hydrogen will be negatively charged is if it follows a metal. So if you have something like LiH, that is lithium hydride, if hydrogen comes first, it's going to be a positive guy in that sense. So there is sort of a negative version of hydrogen. It's really kind of the only element that could kind of go sort of both ways, positive and negative in that particular case. All right, so let's talk specifically about type 1 compounds. As I mentioned before, these are the guys where you look at the metal and the metal basically ticks off of the group 1, group 2, or group 3, zinc, cadmium, or silver. The good news is once you pretty much identify the metal as being in one of those spots, group 1, group 2, or 3, zinc, cadmium, or metal, you pretty much don't have to worry about anything else. You could roll right into the naming part of it. And the naming part is pretty simple. We use, again, the whole name of the metal, or the positive guy. And then really the non-metal gets the IDE treatment at the end. And that's it. It doesn't matter if you got like 40 metals. It doesn't matter if you got like 20 of the non-metal guys, positive guys. It doesn't matter how many you have of each of them. That's pretty much how you go about naming these guys. Whole name of the metal, non-metal gets the IDE. Like, for example, the one that we just had up a second ago, CaF2. Once I look at this as calcium, which is a metal, this is fluorine, which is a non-metal. When I look at calcium, I know it is a member of group 2, which means it has a fixed charge. That's all I need. At that point, I go with the whole name of the metal, which is calcium. The fluorine, if I don't lose the I there, ends up with the IDE at the end of it, and it becomes calcium fluoride. Same thing earlier, we saw NaCl. When I look at this, Na is a metal, Cl is a non-metal. That tells me it's an ionic compound. The sodium, which is group 1, has a fixed charge. That tells me it's a type 1 compound. And that's all I have to worry about, sodium chloride. Question on that there. By the way, a very common mistake, right? We see here again that there's a 2. There is no prefix. People, for some reason, always want to throw prefixes into their naming. And if you do that in this situation, you get an X because it is wrong. So it doesn't matter how many you have of the metal. It doesn't matter how many you have of the non-metal. It has absolutely no effect on the name. It's just the whole name of the metal, IDE for the non-metal. The only reason, obviously, we have the 2 is for what we talked about earlier, to balance out the charge, right? And allow everybody to get to basically noble gas configuration. Has absolutely no effect. Don't use prefixes here. Any questions on that? Yeah. Yeah, so what was talked about here, yeah. So yeah, that's what it's talking about here. Basically, it has a fixed charge. And if you had just the cation by itself, you would just name it like we saw on the previous slide, you know, like if you had just Ca2 plus by itself, you would just call it the calcium ion. Or if you had the F minus by itself, you would call it the fluoride ion. And basically, that's what we're kind of doing with type 1. It's just kind of putting those guys together, you know, and put both of those names basically together when they come together in an ionic compound. Other questions? Now, as we talked about a second ago, when we do look at a formula for an ionic compound, always should equal 0 and should never, ever again have any type of overall charge. But it is important to remember again that it is, as I said earlier, really made up of 2 things that do have charges. So again, if we were to analyze sort of this Ki, we would look at the K, and that is potassium, which is a metal. This is iodine, which is a non-metal. Again, the potassium is the most important thing. We see that it is a member of group 1, which really means it has a +1 charge. Iodine is a member of group 7, which means it has a -1 charge, which is again why when we put them together, we just need 1 of each in the formula. And really at this point, once we identify this guy as being really a type 1 compound, that's all we need for the name. We go with the whole name of the metal, again, IDE on the non-metal, and that is all you have to worry about with type 1 compounds. Any questions on that? Now, if you were asked to write the formula for the cation, you would write this guy right here. This would be the proper formula for writing the cation formula. It again has the charge associated with it. And if you were asked to write the formula for the anion, you would write what is here, maybe not that big, but you would write something like that with the negative charge. So again, it's really important. And sometimes you are asked to, and a lot of times you're asked to write really the formula for the entire compound, the ionic compound coming together. But sometimes you are asked to write the formula for either the cation or the anion. So again, any type of ion that you write the formula for should have charges, but when you put the positive and negative guide together, it should never have a charge, should equal 0. All right, why don't we try some of these here, and then let me give you some names, and you could go with some names. Let's go with Let's go with magnesium phosphide. Let's do sodium oxide, and let's do aluminum. Let's do aluminum sulfide. All right, guys on the left, proper name, guys on the right, proper formulas. Okay, let's take a look, see how we're doing. So we'll start here on the left there. So again, first thing you want to do really is kind of identify. So K is potassium, which is a metal. Cl is a non-metal. That automatically tells you you're dealing with an ionic compound, which means it should be a type 1 or type 2 compound. When we look at it, again, it's always the metal that is the most important. And we see here potassium, which is group 1. We know because it's group 1, it has a fixed charge of +1. And that would be our cation there, our K+. The Cl, which is group 7, has a -1 fixed charge. And again, that is why we need one of each of those, the anion being Cl-. Really, at that point, once we recognize it as a type 1 metal, that's all we need. We're going to go with the whole name of the metal, which is potassium. And chlorine becomes chloride, IDE at the end of it, and we end up with potassium chloride. Any questions on that name there? Looking at the second one, we see zinc, which is a metal. We see sulfur, which is a non-metal, again telling us that it is ionic. Looking at the metal is the important guy, that is zinc. We find zinc on the periodic table in the transition metal region, but is one of those three that we talked about earlier that actually does have a fixed charge. So because it does have a fixed charge, that means that it is a type 1 compound, and we would roll with zinc, and sulfur becomes sulfide. Where the cation here is +2. The anion is sulfur, which is group 6, which has a -2 charge. Again, why we just need one of each of them when we put it together in terms of the formula. Any questions on that particular one? So remember, zinc, cadmium, and silver, although they are transition metals, they have fixed charges, so they really fall under type 1 sort of naming. Here's one very similar to what we saw earlier. We see calcium, which is a metal. We see Br, which is a non-metal. Again, tells you it's ionic. Focusing in on the calcium, which is the important guy there. That is group number 2, which means really it has a +2 charge. The bromine has a -1 charge. That is why there are 2 of them to balance out the charge that is there. Again, if you were to write the formula for the anion, it would be just Br- if you were asked to do that, not like Br2- or anything like that. So it would just be Br-. In this case, really all we need to know is that calcium is a +1, +2 charge, and a fixed charge, which means this would be calcium and this would be bromide. Again, the 2 has no effect on the name here. Any questions on any of those names? Okay, when you're going backwards here from the name to the formula, we really just want to write the basic units of each of these things. So again, when you see magnesium phosphide, that magnesium is a metal, phosphide is really phosphorus in the periodic table, which is a non-metal. So again, it's ionic, which means you should have ions. Magnesium is group number 2, which means it does have a +2 charge. Phosphide on the periodic table is phosphorus, which is group 5, which means it has a -3 charge. In this case, we want to put these guys together to get us to 0. Easiest way to do that is to get everybody basically to 6. So for magnesium to get to 6, we don't need 1 or 2, but we actually need 3 magnesiums to get us to +6. To get the phosphorus to -6, you need 2. And we end up with Mg3P2. Any questions on that there? Now, sometimes people will tell you, hey, just like do the crossover move, like bring that down there and that down there. Or if you have the formula like we had with calcium bromide, Bring that way and that way. And that works like 95-ish% of the time. It does not work 100% of the time. So if you want to do that and 90-ish or so, 95% is good for you, then you can just blindly do that. You'll get most of them right, but there definitely is a lot that it will not work out correctly. So it's best to keep in mind to try to balance out the charges rather than just blindly kind of moving the charges up and down. But it does work a good amount of the time, but not definitely 100% of the time. Yeah. The easiest way, if they're not the same charge, obviously, is just really usually just to multiply them together, the two numbers, and that gives you probably your lowest common number there to get you to there. Other questions? Okay, so looking at sodium, which is a metal, oxide is non-metal oxygen, sodium is +1, and oxygen is group 6, which is -2. In this case, we actually need more of the sodium to balance it out to get us to +2. So we actually need 2 of them, and I'll just write it above here. We get Na2O would be our formula in this particular case. Any questions on that one there? Again, you could also see in this case, the sodium has 2 of them, has again no effect on the name. As you can see, it's not disodium or anything crazy like that. It's just sodium when we name it. Lastly, here we got aluminum, which is group 3, has a fixed charge. We got sulfide, which is -2 from group 6. Same idea here, kind of like the first one. We want to get really the 6 to balance it out there. So to get our aluminums to 6, we actually need 2 of them. To get our sulfurs to 6, we need 3 of them in this case. Any questions on type 1 naming here? So pretty straightforward if you don't try to screw up by doing all kinds of other things that people always want to do when they're naming, putting weird things in the names. All right. Let us then talk about type 2. I left one off. Oh, that's bad. BaH2 here. I guess we'll do that one before I left. BaH2 is barium, which is a group 2. And H is really a non-metal here. This is a case where hydrogen is actually coming second in the formula. And in this case, we still look at the metal. And this is barium hydride. This is a case where hydrogen actually is -1 in this case to balance out the +2 charge that we see with the barium. So when you have hydrogen, as I mentioned before, coming after a metal, it will be the negative version of hydrogen. And again, we name it like all the other negative guys, ID at the end of it. So barium hydride, same rules apply, even though there's more than one hydrogen at the end there, no effect on the name. Now I think we got them all. Any questions on any of those there? Okay. All right, then let's talk about type 2 compounds. So type 2 compounds are pretty much identical to type 1 compounds, except it is the metal that's important. And in type 2 compounds, when we have that metal and non-metal, our metal here is typically a transition metal or to the right, which means it can have a variable charge, positive charge. So if we look at something like what we see here, which is FeCl2, first off, we can still identify it kind of the same way as we did before. We see Fe, which is iron in a metal. We see Cl, which is chlorine, which is a non-metal, automatically tells us we're dealing with an ionic compound here. That means we should automatically look at the metal. And when we look at the metal, it is iron, which is dead center in the transition metal region at number 26 up there. And because of that, what that's a signal to you is you are dealing with a type 2 compound. And what that means is that iron could have multiple types of charges depending on the situation. So what you need to do is basically figure out what is the charge on the iron. The good news is always in a type 2 situation, you will always know what the charge is on the negative guy. So when we look at the negative guy here, that is Cl, which is group number 7. That means that Cl should have a -1 charge. In this particular case, we don't have 1 Cl, but we actually have 2, which gives us a grand total of -2. Because this is an ionic compound, it needs to equal 0. So that means my one iron in this case must have a charge of +2. So you kind of go work backwards from the negative guy to figure out what the charge is on the positive guy. And once you have the charge on the positive guy, we name it pretty much identical to how we name type 1, except that we use a Roman numeral to indicate the charge on the metal. So we still use the whole name of the metal. We still non-metal with the IDE at the end. The additional thing is we do use a Roman numeral here in parentheses to indicate the charge. So if we were to do that, whole name of the metal is iron, Roman numeral 2, not for how many irons we have, but because of the charge that we have on one individual iron atom, or ion in this case. Even though, again, we have 2 Cl's at the end, not going to affect the name. We're still just going to call it chloride with the IDE at the end of it. And this would be iron 2 chloride. So a couple of very common mistakes that people make with this is they think the Roman numerals like how many metal atoms there are ions there are, but it actually is if you took the positive guy out with the positive charge, just one of them, what the actual positive number is on it, and that is what should go into the Roman numeral. Any questions on that? All right, so for example, if we had this guy here, what would this guy be called? So Pb is lead, and that is a metal. O is obviously oxygen, which is a non-metal. Lead is one of those guys that technically really are not a transition metal, but are found just to the right on the periodic table. And they're underneath the staircase where tin is, Sn, and antimony and lead and bismuth. Those guys do have variable charges. They are actually metals below that staircase. So they do fall with type 2 compounds. So when you see lead, it is really a type 2, which means, again, it can have multiple types of positive charges depending on the situation. So what that means is we want to think about lead and what the charge is. There's actually only one lead there. There are oxygen, which is group 6, that has a -2 charge. And in this case, there's not one of them, but there's actually 2 of them. That gives the negative side kind of a -4. That means that the lead in this case is actually +4. And the proper name here should be lead Roman numeral 4 because of the charge. And again, it would be oxide regardless of the 2 that's there, has no effect on the name. This is a prime example that if you just blindly move the charges up and over, you would get the wrong answer. You would end up with like lead 2 or something like that, which would be incorrect in this case, and also the wrong charge on the oxygen. So really important to make sure that you think about getting everybody to 0 and what it actually is. Any questions on that there? Now, there is sort of an older way of naming, which we won't use in his class, and most classes you don't really use it too much, but it still does pop out in some books and stuff like that. And instead of using Roman numerals, there's sort of a historical type name that we use for elements, and guys that have the larger positive charge ends in ic. The one with the smaller positive charge ends in ous. So like iron 3 would be ferric, while iron 2 would be the ferrous. Ion is sort of an older way of naming. We won't really use this here. We will use strictly Roman numerals to name these type of guys. Another very important one, which is mercury, is kind of a weird one. Mercury, Hg2 and Hg2. These guys here are mercury 1 and mercury 2. Oddly, the guy that has the most 2s is mercury 1. Mercury Roman number 1. The guy that has just the 1 2 is actually mercury Roman numeral 2. The reason for that is mercury 1 comes as a dimer. It's basically 2 mercury 1s hooked together. And that is why it has a +2 charge and then 2 on the bottom. You may be asking, how would I know the difference? That 2 will stick around. So if you had something like this, This would be Mercury 1 oxide because the 2 is on the bottom, +2 -2, versus this guy here, which would be Mercury 2 oxide. Again, no 2 on the bottom. So the 2 does hang around, and that's how you kind of tell the difference. Any questions on that there? All right, so here's again how we'll use these guys with the Roman numerals. This is the older way of naming. As you can see, a lot of it is based off of sort of the historical names and stuff like that. All right, so as I mentioned earlier, we basically use the whole name of the metal with the type 2. We use our Roman numerals. And we use our non-metal with the IDE at the end of it. And again, the Roman numeral, the charge on, really the positive charge on one cation. Yeah. Not the grand total, not how many you have of it, but if you just took one of them by himself, what the positive charge is. All other rules still apply. If you got more than one metal, doesn't affect the name other than you need the Roman numeral. And obviously, if you have more than one non-metal, does not affect the name. No prefixes should be used here either when you're naming these guys. All right, so let's try some here. I'll give you some names. You could write those. Let's do nickel for chloride. Chromium 2 nitride and copper 1 oxide. All right, names on the left, formulas on the right. So is a metal. Cl is a non-metal, tells you it's an ionic compound. We're going to look at CO, see it dead there in the center of the periodic table, transition metal. That tells us that it is a type 2 compound, which means we need to figure out the charge. So we may not know the charge of cobalt, but we should know that Cl is group 7 and it has a -1 each. There are 3 of them, which means if you drew them all out to visually see it, that is a -3 overall charge, which means in this particular case, our cobalt must have a +3 charge. That would then give us the whole name of the metal, which is cobalt. Roman numeral 3 for the charge on the cobalt, and then chloride at the end there. Again, the +3 charge is where we get the Roman numeral from. Any questions on that name there? Look at the next one. Cu is copper and I is iodine, which is obviously a non-metal. Our copper also in the center there of the transition metal region should tell us that it is a type 1. That means copper may not know the charge, but looking at the iodine, which is group 7, we do know it has a -1 charge. That means pretty simply here, our copper should be carrying a +1 charge in this case. That means we're going to go whole name of the copper. We're going to Roman numeral a 1 because of the charge, and iodide at the end here. Any question on that name there? Lastly, we see Sn, which is tin, which is a metal, and we see Br, which is bromine, which is a non-metal, tells us it's ionic. The tin is one of those ones that are technically not a transition metal, but are to the right of the transition metals below the staircase. So it does have multiple types of charges. Following our same approach here, not sure what the tin is. We do know that bromine there is group 7, which has a -1 charge. And again, if we just drew out all of them, that is -4, which means our tin is carrying a +4 in this case. That means that this should be tin Roman numeral 4 and bromide at the end. Again, no prefix or anything like that, even though there are more than one of those guys. Any questions on any of those names? Okay, when we look at the name here, we see nickel 4. That tells us it really is a transition metal. The good news is it also tells us what the charge is on the nickel. It means it has a +4 charge. Nothing to have to figure out there. Chloride is group 7, which has a -1 charge. So in this case, to get us to 0, we do need 4 of the Cls to basically balance out that -4 or +4 charge. Any questions on that one? Looking here, chromium 2. Again, the chromium 2 tells us we have a chromium with a +2 charge. Nitride is nitrogen on the periodic table. That is group 5, which means it has a -3 charge. Again, when we put these together, we want to get to 0. So 6 looks like a magic number there. We would need 3 of the chromiums to do that, and 2 of the nitrides gives us Cr3N2. Lastly here, copper 1, same deal, telling us it is a transition metal. It has a +1 charge. Oxide, which is oxygen, is a -2. In this particular case, we actually will need more of the copper to balance it out. We'll need 1 more total. That gives us Cu2O. That is all they wrote on those. Any questions on either of those? They're formulas to names, names to formulas. So type 2, really the only difference is from type 1 is we need to include the Roman numeral, and really naming is just telling people what you're dealing with. So in this case, when you say, hey, it's cobalt 3, I'm dealing with cobalt with a +3 charge. So you have to kind of tell people that. That's sort of why we need the Roman numeral. We don't need the Roman numeral on type 1 because it is understood that they have fixed charges and they can make no other charges. So you don't have to tell people, hey, sodium is going to be +1, because it should always be +1. So in the cases where the metal can make multiple types of charges, we need the Roman numeral basically to tell people which one we're dealing with. Any questions on type 1 or type 2 naming here? All right. So as we saw and as we just talked about, guys that are in group 1, 2, and 3, not to forget our 3 transition metals, zinc, cadmium, or silver here. All these guys are group 1. And again, because of that fixed charge, you don't need to tell people what the charge is. You don't need the Roman numeral. It is only those transition metals are to the right, like tin, lead, and those guys that you do need to include those Roman numerals to indicate the charge on the metal. All right, so take a few minutes here and see what you come up with these guys. Okay, let's take a look. We got HGO. So Hg is mercury, which is a metal. We got oxygen, which is a non-metal. So again, it's ionic. Mercury obviously is a transition metal, which means it can have multiple types of charges. So we do need a Roman numeral here. That's what it should tell us, type 2. And in this particular case, we only have 1 oxygen, which is -2. So this is +2. So this should be mercury Roman numeral 2 oxide. And again, you may be asking, how do I know it's not mercury 1? And the reason is there is not the extra 2 on the bottom, as we talked about earlier. Again, that mercury 1 would have that 2 that hangs around, but it's not here in this case. So it is mercury 2 in this particular case. Looking at the next one, Mg is magnesium. It is bromine, which is a non-metal. Magnesium is the important one. It is type 1 compound, which means we don't need to worry about Roman numerals. We just need to roll out the whole name here because it has a fixed charge of +2, and bromine will become bromide. So magnesium bromide in this case, no Roman numeral needed as it has a fixed positive charge. Now make it a type 1 compound. Any questions on that one? Coming here, we look at lithium, which is a metal, oxygen, which is a non-metal, same deal, always the metal most important. Lithium is group 1, which also means it has a fixed charge. So that's all you need. Whole name of it, which would be lithium, and oxygen becomes oxide. Again, it is a type 1 compound, no need for Roman numeral in this case because of the fixed charge. Cr, which is chromium, F, which is fluorine, metal, non-metal, tells you it's ionic. Chromium definitely is right there in our transition metal region, telling us it is a type 2 guy here. That means it could have multiple types of charges. Looking at the F, which is group 7, has a -1 charge. And there's not just one of them, but there are 2 of them. That means that the chromium here does need to have a +2 charge to balance it out. That would then give us chromium Roman numeral 2, again for the charge. And even though we do have 2 of these, no effect on the name, no prefix or anything like that. So fluoride here, chromium 2 fluoride. Any questions on type 1 or type 2 naming? Again, the key here is really the metal. So whenever a metal is involved, that's really what's going to help you determine how to properly name it, and really whether or not you should put Roman numerals or not is really what's going to help you decide. All right, little decision tree. Let's then talk about type 3 compounds. Type 3 compounds are a little bit different. They contain only nonmetals. So these are our covalent or molecular compounds. These are our guys that are sharing electrons. And these are absolutely the easiest to do and should take you the quickest to do. But they're also the ones people screw up the most on because they want to do all kinds of weird things with it. I've been yelling, no prefix, no prefix, no prefix. These are the ones that you should use a prefix for. So these are the ones that we do use prefixes to name. Things like mono, which means 1, right? Di, which is 2. Tri, which is 3. Tetra, which is 4. There's a table coming up, I think. Penta, which is 5. Hexa, which is 6. Hepta, which is 7. Octa, which is 8. Nona, which is 9. And deca, which is 10. So these are actually the ones that we use prefixes for. The nice thing about this is there's pretty much no need to worry about charges because they're sharing electrons, so there's really no charges. There's no need to balance out things or anything like that. Basically, you pick the right prefix and you use the whole name of the first element, and the second element gets the IDE at the end with the appropriate prefix. So, you know, these are pretty straightforward. You should take you like a second when you see these type of guys to name it. There are a few little rules that we do want to follow with the prefixes and sort of how we go about using them. The first major one, as we will see here in a second, is we never use mono on the first name, but you could use it on the second name is okay. I'm not 100% sure that's still the right table in your book, but it's somewhere in that chapter 5. So for example, if we had CO, we would look at this and there's only 1 carbon, there's only 1 oxygen, they're both nonmetals. This tells us it's a type 3 compound. Prefix for 1 is mono for both, but we would not use mono on the first name, which means for the first element, we just use the whole name like we kind of did before. So that would be carbon. Second name, we absolutely can use the prefix. So we could use mono, and the second element gets the IDE treatment at the end of it. So oxide. And this is the other thing that sometimes happens is when you take a prefix and the first letter of the element, you get a couple of O's that back up. So we don't usually call it carbon monoxide, right? We call it carbon monoxide. So typically in this case, we would get rid of the O that comes off of the prefix, and we would call it like we normally call it, carbon monoxide. So occasionally what happens when you use the prefixes in those first letters is you get like an O and an O like we just saw there. We typically get rid of the first O from the prefix. You also get an O and an A. I'm sorry, wrong way. We get an A and an O. We get rid of the A off of the prefix. 2 I's are okay. Usually we could leave the 2 I's, but usually if we get 2 O's that back up to each other, we get rid of one of the O's, the first one. If we get an A and an O, we get rid of the A off of the prefix, and 2 I's are okay. How we name it is pretty much like I said. You're going to use the appropriate prefix if necessary, the whole name of the first element, and then you're going to use the prefix with the whole name of the second that has the IDE at the end. I won't say whole name, I guess the non-metal name. We'll do it like we did before. Non-metal with the IDE at the end is a better way of saying that. So the nice thing about these, like I said, is you really don't have to figure out charges, you don't have to figure out balancing things. You pretty much just need to write what's there and not have to worry about any of those type of things. So here are our prefixes, as I mentioned before. Again, getting rid of some of the weird backing up of a couple of vowels. And again, it's usually in 2 O's together, an A and an O. That's an issue. Now, some things, as I mentioned earlier, do roll with their normal names. So, dihydrogen monoxide or hydrogen monoxide, it is water, ammonia, and CH4 is the other one, which is methane. Now, let's talk about one other sort of exception, if you will, which is hydrogen that comes first. So if we had something like HCl, hydrogen is a nonmetal, Cl is a nonmetal. So in your head, you might think, well, I should maybe use sort of type 3 naming. And for a lot of reasons that we're going to talk about a little bit later on in some chapters, hydrogen that comes first is almost treated like a type 1 compound, even though technically speaking, it's not a metal or anything like that. We usually will look at this and think of it like H plus and Cl minus. So, and again, it's because it's hydrogen. We would actually just call this hydrogen chloride. So hydrogen is a little bit different in the way it's named. It's, even though technically speaking it's a non-metal, it's pretty much named like a type 1 metal. Even if you had 2 of them, for example, H2S, we would call this hydrogen sulfide. So pretty much if you have hydrogen, and we kind of think of this like 2 H pluses and a S2 minus. So it has a lot to do with it being acids, and sort of a lot of acids basically work this way. But hydrogen is kind of a weird nonmetal when it comes first. We think of it more like a cation and a positively 1 charge, even though technically speaking, HCl, they're sharing electrons like we drew Lewis structures the other day, and they're all sharing electrons. But when they kind of go into water, for example, they sort of act almost like a cation. So they're sort of named that way. If these were gases, they would still be bonded together. So hydrogen is kind of a weird exception. So if you have hydrogen that sort of comes in front of like a nonmetal, we do just call it hydrogen, and whatever the negative guy is, and treat it more like an ionic compound than sort of a covalent compound where they're sharing electrons. Any questions on that there? Okay. All right, so why don't you take a couple minutes here, or a couple here, and do these guys. We'll also give you some names. Let's do nitrogen pentoxide. Let's do carbon tetrachloride. And let us do dioxygen trisulfide. All right, names on the left, formulas on the right. I think we're going to lay it up here for now here, since we're getting to the end of lecture. What we're going to do is we're going to continue lecturing and finish up the rest of naming. We've got 2 more types to talk